Welcome back, water resources students. We're going to have what I think will be a very quick lecture here on land use hydrographs. We touched on this briefly at the end of the previous lecture. Now I want to just go a little more in depth because I think this is a great example of how the watershed factors conspire to govern surface runoff, but it's also a very applicable um, applied example of how water resources principles are sort of applied out there in the real world. All right, so we've already discussed in the previous two lectures the watershed factors. So I'm not going to go over that again here. It's just to sort of cue you in that we're continuing to talk about these watershed factors. Okay, so where we want to focus our discussion in this lecture is on this hypothetical hydrograph. So a hydrograph, as you'll recall from an earlier module, is a graph of either discharge or stream stage on the y-axis versus time on the x-axis. In this case, we're measuring discharge, but it really doesn't matter for the discussion of its discharge or stage. Discharge is stream flow per unit time, so like gallons per second. We wouldn't usually use gallons per second. We'd use cubic meters per second or cubic feet per second, but gallons probably make more sense to you intuitively. So let's say gallons per second. Or it could be depth. How deep did the stream get at a specific spot along its course, like a gauging station? So even though this says discharge, let's talk about what I'm going to go through here in terms of depth, because it'll make it a little more intuitive to you. All right, so we've got four hypothetical land uses: urban, agricultural, a mix of agricultural and forest, and forested. And we're going to pretend that this is in one watershed and everything else is equal. All the other watershed factors are equal. The only thing we're changing for our hypothetical watershed is what would the stream flow look like? What would the flood response to a certain rainfall look like if it were all urban? Or if we wave our magic wand and switch it to agriculture? Or if we waved it again and switched it to forest? How would that change in land use in our hypothetical watershed affect the way that precipitation is translated into a stream flow and a flood? All right, so let's start with the urban setting here. And let's just have a hypothetical rainfall. So usually we draw a rainfall in a hydrograph as sort of bars coming down from the top here. So what that means is along the x-axis, it started to rain here at time 0 because this sticks down even further. At time 1, it rained even harder, and maybe at time 3, it started to taper off, and by time period 4, it was gone. Let's just say these are hours or minutes. It doesn't really matter. All right, but our peak rainfall then occurred here at the second time unit. Where's the peak flow for our urban watershed? Well, here our stream flow peaked right at that point. So it was deep if we look on the y-axis, and that peak was a certain period of time, this period of time, between peak rainfall and peak runoff. And the water rose very quickly and it came down very quickly. And the reason this happens is I'm sitting here on campus in the middle of an urban watershed. When I look out my window, I see concrete, sidewalks, parking lots, streets, roofs on the buildings. All of those surfaces have no ability to intercept water like we can with trees and vegetation and things that we explained in the first lecture in this module, or the ability like soil to absorb and slowly release that water. So all the water that falls on the impervious surface that I'm looking at here in my urban watershed, all that water immediately runs off into a storm sewer. That storm sewer directs that water to a nearby stream, and all that water gets in the stream really quickly and flows. So what we get is a rapid increase in flood stage, a rapid increase in depth, and then a rapid decrease. This is called a flash flood. Now the agricultural watershed's a little different. In the agricultural watershed, we have bare soil, but we don't have much impervious surface other than a few roads here and there and a house here and there. The whole agricultural watershed now are farm fields. So all the soil's out there, but the soil's exposed. Farmers do a good job at keeping all the vegetation off of their fields except for the vegetation they're growing in their crop. So if you've got a corn crop, you've got corn plants, but all the soil in between those corn plants is bare soil. We don't let anything grow in there. Anything in between the corn would be, by definition, weeds. So if the rain happens to fall right on the corn, there's an opportunity there for a little bit of interception, and the water can definitely get to the soil where it can be absorbed. But in between the corn plants, there's no other opportunity for interception. So it's not as flashy a flood as we have in the urban setting. Our peak flood would be right about here. So it's not as deep, and the lag time is longer. Here, our flood from peak rainfall to peak runoff is maybe almost twice as long as the urban watershed. And don't get too caught up on whether it's twice as long or 3 times or 1.5. That's going to vary every watershed, because right now we're just focusing on land use, but in real watersheds, not hypothetical watersheds, we've got climate and topography and geology and soils and all these other variables. That means that the relationships between how much longer the lag times aren't going to be consistent. The point is that this agricultural watershed will have a longer lag time and the flood's not going to be as deep. Let's skip out here to the forested watershed. Now in this case, our peak flow is way, way longer than the peak flow for the urban watershed, and our flood is much less deep. So we have this long, long, long lead up to peak flood, and then it goes down relatively quickly after that. But the whole flood here lasts a long time. And so it never gets as deep, because what we're doing is we're taking the same amount of water. Hypothetically, let's just imagine that under each of these curves, urban, agricultural, ag, forest, and forest, we have the same number of gallons of water discharged in the stream. It's just in this forested setting, because we have the trees, we have the understory, we have all the soil exposed. So we have tons of opportunity for interception processes to occur. We have lots of soil exposure so that that soil can soak up that water and re-release it slowly. And because of all that, the water only makes it to the stream at a slow rate. You know, it takes a long time for that peak to rise, and then it falls, and we never get a great big flood. So in the ag forested watershed, we're just sort of halfway between ag, where we've got some agricultural fields that are going to act like the agricultural example, and then maybe we've got some forested plots that are going to act like this. And when you average them out, you get something that's here in between. I'll color it purple, where we get, you know, a longer lag time than the agricultural, but not as long a lag time as the forested. And the point here is land use is the one variable that humans affect a lot. I mean, think about it. We have formed the whole Great Plains from wet prairie, basically one great big prairie wetland, and we've drained all those wetlands. We've plowed those prairies under and replanted them as corn and soybeans and some other crops. So we converted the prairie, and a prairie is going to act like the forest. So we've converted the Great Plains, the whole center part of the U.S., from something that's going to act like this forested hydrograph to something that's going to act like this. So we're not talking about small changes that humans make around the edges. We're talking about wholesale differences. And then urban settings, things like that. So we have a lot of influence over land use, and that has a big impact on the hydrographs in these watersheds. All right, that's where we'll end it for this one. I thank you for your